Welcome. In this video, we'll build a complete understanding of convolutional neural networks from the ground up, covering convolution, pooling, the full forward pass, and exactly how backpropagation flows through every layer. A standard MLP treats an image as a flat list of pixels. A 224 by 224 RGB image has over 150,000 inputs, and the first hidden layer alone would need 154 million weights. CNNs solve this with parameter sharing. A single 3 by 3 kernel scans every position of the image using the same 9 weights, detecting the same feature anywhere it appears. This is translation invariance, and it's the key insight. Convolution operation works like this. We place a 3 by 3 kernel at the top left of the input, multiply each kernel weight by the corresponding input value, sum them all up and place the result in the output feature map. Then we slide the kernel one step to the right and repeat. This kernel shown here is a horizontal edge detector, the Sobel filter. Notice how large positive values appear where there are strong left to right intensity changes, and large negative values where gradient goes right to left. One convolution layer typically applies dozens of kernels simultaneously. Each kernel produces its own feature map. Early kernels learn simple detectors, horizontal edges, vertical edges, color blobs. Deeper layers compose these into textures, shapes, and eventually high-level object parts. All of these kernels are initialized randomly and learned entirely through backpropagation on the training data. After each convolution, we apply RALU activation. RALU simply clamps all negative values to 0. This introduces nonlinearity. Without it, stacking multiple convolution layers would be equivalent to a single linear transformation. The derivative of RALU is straightforward: 1 for positive inputs during the forward pass, and 0 for negative inputs. This zero gradient for negative inputs is called the dying RALU problem and will matter during backpropagation. Max pooling downsamples the feature map. We slide a 2 by 2 window across the output with stride 2, and keep only the maximum value in each window. This halves the spatial dimensions, reducing computation and making the representation more robust. 2 small shifts if a feature is detected 1 pixel away. Max pooling still picks it up. Critically, during backpropagation, only the maximum neuron in each window will receive the gradient. All others get 0. Putting it all together, a typical CNN stacks convolution and pooling layers. Each convolution layer learns increasingly abstract features. After the final pooling layer, we flatten the 3D feature volume into a 1D vector and feed it into fully connected layers, just like a standard MLP. The final output layer uses softmax to produce a probability distribution over n classes. The softmax function converts the raw output targets into probabilities that sum to 1. Cross-entropy loss then measures how wrong our predicted distribution is compared to the true one-hot label. The beautiful result is that the gradient of the cross-entropy loss with respect to the targets is simply the predicted probability minus the true label, a clean signal that gets larger the more wrong we are. Backpropagation is the chain rule applied layer by layer from the output back to the input. Starting from the loss gradient, we propagate through the fully connected layers using standard matrix operations. Then we reshape the gradient from 1D back to 3D and continue backward through max pooling, RALU, and convolution. Each layer has a specific backward rule, and each layer's backward pass produces 2 things: the gradient for its own parameters, and the gradient to pass further back. The backward pass through a convolution layer has a beautiful symmetry. The gradient with respect to the kernel weights is computed by cross-correlating the incoming error signal delta with the original input. The gradient with respect to the input, which must be passed further back, is computed by convolving delta with the kernel rotated 180 degrees. This is called a full convolution because it requires padding. In other words, the backward pass through a convolution is itself a convolution, the same hardware-efficient operation in both directions. Here is the backward pass through a convolution shown as a concrete convolution operation. We have our original 3 by 3 input I, and the upstream gradient delta A2 by 2 matrix or error signals. To compute how much to adjust the kernel weights, we treat delta as the sliding kernel and cross-correlate it with the original input. At each position, we multiply delta element-wise with the patch of input under it and sum. Position 0, 0 gives us 2 times 1 plus 5 times 1 equals 7. Position 0, 1 gives 4 plus 2 equals 6. The result is the 2 by 2 gradient matrix DL over DK, same shape as our original kernel. This tells us exactly how much to nudge each kernel weight. The second backward pass computes the gradient with respect to the input This is what gets sent further back to the previous layer. We take delta, pad it with 1 0 on every side because we need a full convolution, and flip the original kernel 180 degrees. Our kernel was 1 2 3 4. Flipped it becomes 4 3 2 1. Now we slide this flipped kernel over the padded delta exactly like a standard convolution. At position 1 1 in the padded grid, delta is 1, so it receives contributions from all 4 kernel positions. 4 times 1 plus 1 times 1 equals 5. That 5 is the gradient flowing back to input position 1 1. At corners with no delta signal, the gradient is 0. The output is a 3 by 3 matrix, same shape as the original input, ready to propagate backward to whatever layer came before. So the backward pass through a convolution is itself a convolution. Cross-correlate delta with input for kernel grads. Convolve padded delta with flipped kernel for input grads. Once we have all gradients, we update every weight in the network by taking a small step in the direction opposite to the gradient. The learning rate eta controls the step size. In practice, we use mini-batch SGD. We average the gradients across a batch of images before updating. This reduces noise compared to updating after every single sample, while being far more efficient than waiting for the entire dataset. After thousands of such updates, the kernels converge to filters that minimize the training loss. Let's recap. CNNs exploit parameter sharing and translation invariance to process images efficiently. Stacked conpool layers build a hierarchy of features from edges to complex shapes. Backpropagation flows cleanly through every layer through the cross-entropy gradient, through ReLU masks, through max pool winner routing, and through the elegant full convolution backward pass. With SGD tying it all together, CNN learns to see. If you are to create your own animated video explainers like this one, check out Samity at samity.com.